Okay. Can people see my screen? It should be a VS Code session. Great. Okay. Let's get started. So I'm going to do a quick demo. I'm going to prove something for you in Lean, just to show you what it feels like. Don't expect to understand everything that goes on in this. If you haven't used Lean before, there will be time enough to do that all this week. It's really just meant to give an impression of what theorem proving in Lean feels like. I'll also admit I showed Patrick earlier a preview of this demonstration, and he said that it was a lie. Perhaps it was a nice lie, but it's still a lie, in the sense that this is a demo where everything goes well, and I do just want to warn you that your experience using an interactive theorem prover will probably not go as smoothly as things go right now. Well, that assumes things go smoothly. Okay, so what's going on here? You can see from this line here that we're planning on proving a theorem, and we've given that theorem a name, Infinitude of primes. And then after that name, we've written a colon, and after the colon comes some statement, which is what we're going to try and prove today. And hopefully that's fairly readable to almost anyone as a reasonable statement of the fact that there are infinitely many primes. So for all natural numbers n, there exists some p greater than or equal to n, such that p is prime. Okay. After the statement of the theorem, we've written a colon equals, which means that we're now ready to give the proof. And after the colon equals, we have a begin end. Now, there's going to be lots more discussion of what exactly begin and end really mean. And in fact, there's going to be lots more discussion of how they work under the hood if you go along to Rob's talks. But for now, you can just think of them as completely analogous to a /begin proof /end proof environment in a LaTeX file. It's just marking out where we're going to write the description of our proof. Before we start writing anything here, let me just point out a few things going on in this screen. If you haven't used VS Code before, the first thing to know is just the left-hand side of the screen is essentially a text editor where we write our proofs. And the right-hand side is the Lean info view where we get feedback from Lean about what's going on. There are a few things to note at the top of this file before the theorem statement. First of all, we've imported a file called data.nat.prime, which contains things, for example, like the definition of the word prime. Of course, there are different notions of primality that Lean knows about. There are prime natural numbers, there are prime ideals, possibly other things as well, and we need to tell Lean about that. In fact, this file data.nat.lean that I've imported contains this very same theorem, but I'll promise not to use the proof of that theorem that we've imported. I've also got an open statement here where I'm opening a namespace. The namespace is nat, and this is just to disambiguate which prime we're talking about. You can see that if I put my cursor over the word prime, a little tooltip pops up with some help, and you can see there the full name of this declaration is nat.prime, so we might guess that it's the version of primality that's talking about natural numbers. It's important to know everywhere in Lean, you can always hover your mouse over something and hopefully get some helpful text explaining what's going on. Okay, that's all of the setup. I think it's time to actually prove the theorem. As soon as we click inside the begin end block, over on the right-hand side of the screen, the goal appears, which is Lean telling us where it thinks we're up to in the proof, that is, what remains to be proved. And what's written here at this point is just a very close restatement of the original statement we gave over in the editor on the left. You can see a few differences, though. We just wrote originally for all n, and in the info view, that's been expanded out to say for all n a natural number. So Lean is assuming that we're talking about natural numbers. And I guess the other change that you can see here is that where we simply wrote there exists p greater than or equal to n, Lean has parsed that out into two pieces. It's saying there exists p some natural number, and separately, there exists h, a proof that p is greater than or equal to n, and then finally such that p is prime. But you can see that pretty much it's interpreted the statement the way we intended. Okay, the very first thing a mathematician would do looking at this statement is they would say, well, let's take n to be some natural number. And that's exactly what we do inside this begin end block. We write intro n. So this is an example of a tactic, and the tactic script that we write inside begin end blocks typically consist of some sequence of tactics. Now, the important thing is that you can click before and then after each tactic invocation, and the info view on the right will update to show you what Lean thinks has changed. And you'll see the difference is that before the intro, we had this universally quantified statement as the goal, but after the intro, now we have some fixed n, a natural number, as a local hypothesis, and the goal, which is what comes after this entails symbol, is simply some statement about that particular natural number. Okay, so that's exactly the same as what would happen when we say, let n be a natural number in informal mathematics. So at this point, we probably should stop and think for a moment about what we're going to do, what the mathematics is here, and we will just follow, I guess, a proof that goes all the way back to Euclid and use some factorials. So the idea is we're going to take our number n, we're going to look at n factorial plus 1, we're going to take some prime factor of that, and work with that prime factor as our p. So in order to do that, we need to define some things. So I'm just going to write here let m colon equals fact n plus 1. And when we do that, we gain in the goal view a new hypothesis, m, along with its definition. Now, of course, here I had to know something that you couldn't necessarily have done as a complete beginner, which is I had to know that fact was the command, or was the function, which computes the factorial of a natural number. I can verify that it's the thing that I wanted by hovering the mouse over it and checking what pops up. But we'll talk later and in other sessions about how to actually go and find things that have been defined elsewhere. But for now, let's just pretend we knew that fact was what we were after. And similarly, after we've defined m, let's define p, and I'm going to define that to be the minimum factor of m. So again, I've had to use my knowledge that nat.minfac was the function I wanted, and we can see from the text there that it's meant to return the smallest prime factor. Okay. So at this point, we want to declare that this p that we've just constructed is the p that satisfies this existential statement. And so we can achieve that by typing use p. And you'll see here that before that tactic, we had an existential statement. And after that use p, we just have the condition about the p that we chose to satisfy that existential statement with. Okay. We've got two things left to prove. P is greater than or equal to n, and P is prime. And since we have two things to prove, let's write split, which now gives us two separate goals. Notice that the hypotheses have actually just been repeated verbatim in both cases. They might diverge afterwards, depending on what we do. And but in each of the goals, we've just got part of the statement. Anytime that you find yourself in this situation where you're working on multiple goals, it's a good idea to structure your proof in a way that's readable. And the right way to do that is to use braces. So here, when I enter a pair of curly braces and put the cursor between them, we're back down to one goal. It's just focused on whatever the first goal was. And I can use another set of curly braces for the second goal. And in fact, I might write sorry inside each of those curly braces. Now, sorry is a magical tactic that proves anything. And so when we put our cursor at the end of the begin-end block now, we get the celebratory statement, goals accomplished, which we feel very happy about and decide that we can go away and be done with this. But of course, that's premature because we've cheated and used sorry. And you'll notice that back up here at the theorem statement now, there's a little yellow squiggly line underneath and a warning that this declaration uses sorry. And in fact, if we go on to import this file now in any other file, there'll be a warning that appears in that file as well, telling us that the thing we're importing uses sorry, and our sin will not be forgiven. So why do we use sorry at all? Well, the point of sorry is just that when you're working on a proof, there are often many different threads of the argument going on at once, and you want to be able to jump between them and work on different things in different times. And sorry just lets you stub things out that you're planning on going back to and working on later. Okay. In fact, I happen to know that the way the rest of the proof is going to go, the goal in the second branch here, that P is prime, is actually a fact that we're going to need to use in the first branch as well. And so I'm going to go back a few steps here before the use p, and I'm going to add that as an extra fact. I'm going to write have pp colon prime p, and I'll write again colon equals sorry. So what this does is it adds a new hypothesis to our goal state at this point in the proof. It names that hypothesis pp, and it's meant to be a proof that p is prime. But for now, I've just proved it with sorry, and I'll have to come back to that later. Okay. Now, why am I saying sorry at that point rather than actually going and proving it? Well, the reason is that this should be very easy. I defined p just a moment ago to be the minimum prime factor of m, so of course p is prime. Now, a good principle anytime you're working on a proof in Lean, or in fact when you're working on a proof in mathematics, is that the easy bits of the proof, the bits you're sure are going to work and can't possibly be difficult, you should leave for last, and you should concentrate on getting the difficult things done first to make sure that your plan for the proof is sound in the first place. So it's actually a very good idea to put a sorry here for the easy steps and proceed on to the more difficult parts. Okay, so clearly the interesting part is here, proving that p is greater than or equal to n. If we think about how the proof is meant to go, the traditional thing to do at this point is to say, well, we're going to do a proof by contradiction. And so now we've gained a new hypothesis, the fact that it is not the case that p is greater than or equal to n, and our new goal is to prove false. We now get to the actually interesting part of the proof, and the general framework here is that we're meant to prove a series of statements about divisibility. We're meant to prove, first of all, that p divides factorial n plus 1. And let me just write by sorry there. And we're meant to prove separately that p divides factorial n. And let me again write by sorry there. Putting those two facts together in a fairly easy way, we should prove that p divides 1. But again, let me write by sorry. And that should then give us our contradiction, because we proved earlier that p was prime. We've hopefully just obtained the fact that p divides 1, and that should give us what we want. Great. So at this point, we should be feeling pretty confident. We've written the overall structure of the proof, and we've got a whole lot of sorries, but that's okay, because all of the sorries we have a plan for, they all seem pretty plausible things to prove. And in fact, at this point, we could parallelize. If we've got some collaborators or students or helpful people on Zulip, we could actually farm out some of these sorries to other people and get them all done. Instead, what I'm going to do is essentially farm out these sorries to the computer. When we are in this state right at the end here, before the final sorry, remember what do we have? Well, we've got the fact that p is prime, and we've got the fact that p divides 1, and we're hoping to get a contradiction from that. So I'm just going to ask the computer to use the tactic library search, which says, please go and search the library for some lemma that closes the current goal, and you're allowed to use any of the local hypotheses we have at the moment. And sure enough, a little blue squiggle turns up, saying that library search succeeded. And over here in the info view, we have the advice. Try this. Prime dot not divide 1, pph. And that sounds very promising. It's some theorem about primes not dividing 1. And indeed, it uses the local hypotheses pp and h that we have available. Great. So we click on the try this, and that automatically substitutes that in to our proof. That was quite a success. So let's continue trying this strategy, putting in a few more library searches. That one seemed to work. That one didn't work, so let's switch that back to sorry for now. That one worked as well. Let's go down here. That one works as well, and let's try up here. Okay, that one doesn't work, so let's switch that one back to sorry. Okay, but that was a great success. Several of our sorries basically got dealt with automatically. Those results had already been proved, and we could look them up automatically. Let's zoom in on this one, which sounds like it's going to be a bit more difficult. And since we expect to do a little bit of work maybe here, I'm going to write a new begin end block to keep the formatting nice and easy, and look inside where I've just got this one goal where I'm trying to prove that p divides n factorial. Now, library search failed to find a lemma that just closed that goal from the local hypotheses. And so the next thing I'm going to try as a fallback from library search is suggest. Now, suggest is actually quite closely related to library search. The difference is that it returns a possibly long list of ideas it has of possible lemmas from the library that might be relevant. And often it's full of junk, and often it's actually not useful at all. But sometimes it's worth having a look through to see if you find anything relevant. And in fact, the very first one here actually looks quite promising. We don't need to completely understand it, but it says refine pp.dividfact.mpr. Now, who knows exactly what that means, but it does have the phrase divide fact in it, so it's going to be some theorem about dividing factorials. Lemmas in MATLib are named in a very boring, very consistent, and extremely useful way, where the statement of the lemma is usually reflected directly in the name of the lemma. So we can assume that this is some statement about dividing factorials, and since that's what we're trying to prove at the moment, I'm just going to click on that first option and substitute it in, and see where our goals are now up to. So our goal at this point is to prove that p is less than or equal to n. And that is actually pretty plausible because we have the fact that it's not the case that p is greater than or equal to n. So it should just be some easy playing with inequalities, and maybe we can even just use library search at this point to get that result. And sure enough, Lean says, yes, I know how to deal with that. There's some theorem called LE of not G, which, if you think about it, is exactly what we wanted to do. Okay, so we're down to a single sorry. So let's again replace that sorry with a begin end statement and think about what it is we're meant to be doing. Well, library search failed, so let's try suggest instead and see what it comes up with. It's got a shorter list this time. And looking through them, the first and second ones are something to do with actually the definition of being a prime number, which doesn't feel like what we want to use at the moment. But the third one has the name minfac prime, which is extremely promising because it's presumably saying that the minimum prime factor of some number is prime. So since it's got a good name, let's click on that and click after the comma to see what the new goal is. The remaining goal we have now is m is not equal to 1. So why is that? Let's take a moment to stop and understand that. The function minfac that we used before says it returns the smallest prime factor of n not equal to 1. Minfac itself is actually a total function. It's defined on all natural numbers, and for every natural number it returns some other natural number. Now, if you think about it, for 0 and 1, maybe that doesn't make quite so much sense what it should return, and for 1 in particular, it really just can't return a sensible value. There really is no smallest prime factor of 1. But minfac here in MATLib is a total function, so it returns something. I don't know what it returns, maybe 0 or 1 or 37, but it's some garbage value effectively. And that's the reason why we have a condition on the theorem minfac prime. It will only promise that the value it returns is prime if the value that was handed to it wasn't the bad value that could result in garbage. Okay, so that's why we now have a goal, m is not equal to 1. Okay, how are we going to deal with that? Well, let's look at the definition of m. It's n factorial plus 1. And we can immediately see that n factorial is probably quite large, so we're going to prove this by using some inequality. We're going to prove that m is not equal to 1 by proving that it's greater than 1. And the thing that it comes down to is just that the factorial of anything is a positive number, okay? And so that ensures that m is strictly greater than 1. So the key mathematical fact is that n factorial is positive, and then after that it's just some inequalities. So let's state that fact that we cared about. Have factorial n is greater than 0, and let's hope that library search can do that. And indeed it does, it has a suggestion. And now we expected that from this point onwards it was just dealing with inequalities. So at this point we go back up to the very top of the file, we import an extra tactic called linearith, which is a fantastic tactic for dealing with boring inequalities. And we type linearith. Oh, and everything worked. So notice that, again, if we click at the very end of the proof, we have the fantastic goals accomplished announcement. And there are no little yellow squiggles on the theorem statement, and there are no red marks anywhere in the file. And that's the way that Lean tells us that everything has worked, that we really have completed our proof. Okay, that's great. We've got a complete proof, and Lean has certified that this is a satisfactory proof. There are a number of ways in which what we've got written here on this screen is not particularly satisfactory. For one, we've got all these by library searches and the blue squiggly lines on them. So maybe let's quickly clean that up. I'm just going to go to each of those and click on the try this message to substitute in the proof that it found. Oops. Oops. There we go. And in fact, we could do a little bit more tidying up. This begin-end block is actually pretty easy. This begin-end block is a series of tactics that is producing a proof of p divides factorial n. But we might want to reduce that down to a short term mode proof, like we have here or here. And it's pretty easy to do this by hand if you know what to do. But we can also ask for some help from Lean. There's a nice little tactic, show term, which you can wrap around a collection of tactics, and sometimes at least it will print for you an equivalent term that produces the same, that has the same effect as that tactic mode proof. So I can just click on that, and in fact I can just delete the begin exact and end and reduce that down to a one-line term mode proof. We could try and use show term back up here in this block, but it turns out that linearith produces some pretty ugly proofs, and we wouldn't want the term mode proof that linearith produces. So I'm just going to leave this one as is in this proof. Is there anything else we should do before we declare victory and take this as our proof of the infinitude of primes? Yes, there probably is one more thing. This proof is reasonably well structured already. It has some let statements at the beginning, new facts we need along the way, introduced in have statements. And when we reach the point where there are multiple goals, we structure our proof using braces to handle the branches of the proof separately. But we could, of course, also go through this proof and add some human-readable comments that explain what we're doing and explain the reasoning and explain the mathematical intuition and make it easier for a human who comes to this later to follow along. And ideally, we'd do that as well, but I'm not going to do that today. Okay, so that is the end of the little demo. I